We have looked into the news window model or the up-to model. So in this lecture, we talk about risk pooling strategies. So this is actually basically a high-level stock-related decisions. So how the business or the company should organize their logistics network, locations of the storage, and so on. So this lecture is based on the textbook chapter 7, also in the original book by Kashang, in chapter 17, if I'm not wrong. So here I put the optional reading. So it's a pooling principles. So this actually similar content with this chapter, but it's from text from the article perspective to emphasize the main principles and applications. And then we see the agenda in this lecture. We first see what is risk pooling, then we actually talk about different types of pooling. For example, location pooling, virtual pooling, and product pooling, lead time pooling, and capacity pooling. Somehow there's one extra entry. So the learning objectives understand the concept of risk pooling. So we'll talk about that later. Know about different types of pooling. Be able to evaluate the impacts of location pooling. Apply commonly seen pooling principles. We know the real operations environment is always uncertain or stochastic. So the idea behind the risk pooling is to redesign the supply chain, the production process, or the product, or either reduce or hedge the uncertainty so that the firm is in the better position to mitigate the consequences of uncertainties. Then we can talk about this risk pooling from different perspectives. So the different types of poolings may require different levels of change of the supply chain. For example, location pooling may also require redesign the supply chain structure. And then the capacity pooling quite likely will require the production process change. And the product pooling, of course, related to both supply chain, production process, or the product. So we continue to use a Medtronic case. So this medical product producers, they actually uses multiple sales representatives in the field and manages a cache of inventory. A cache of inventory is a quantity of inventory to serve the representative's territory, and there is a single distribution center to serve the entire U.S. markets. So if we try to draw this supply chain, then we have a distribution center, and you have actually star-like supply chains. You have sales reps, 1, 2, 3, 4, and then now we face to the question, should there be one stockpile of inventory per sales representative, or should the demands from multiple territories be served from a single location? So think about the individual sales representatives. Should they all hold their own inventories, or we can actually pool the inventory for multiple territories into a single storage? Or the second question, should there be a single distribution center? A single distribution center is actually current practice, or should this market be divided into multiple distribution centers? So it's a future need actually research. So this type of questions related to apply the location pooling here. So single location into multiple locations, or multiple location storage become a single storage. So next, let's see how to pool the Medtronics field inventory. So pool means put things together or merge some inventories. So the question directly is where to locate Medtronic's field inventory. So field inventory is actually the inventory directly to satisfy individual customers' demands. So let's see the shared inventory in a centrally located and accessible location. So for example, in a back room in a mall or storage room, which multiple representatives can share the location and then can pick up the products quickly. And then control of the pooled inventory will be guided by an automatic inventory replenishment system. So that's actually what we talk about all the time. So we assume you have the possibility actually to implement such inventory policies. So all the sales representatives actually have the access to this automatic inventory replenishment system and can control and can enjoy the benefits of such a system. They cannot just go back to count the items again and again. So now we use this case, continue to show the impacts of the location pooling. So we use the territories inventory or stock control policies. So first, in the current practice, the individual sales representatives carry their own inventories individually, and then we know the order up to level is full, and the units. This actually can be read from your poison inventory function table, and the days of demand is 3.4 divided by 0.29, and then pipeline inventory is always 1 day inventory. And then we think about what if you merge two territories together. So now we have this column. You have two territories share inventory in a common location and expect the demand doubled. And then if you calculate the service level, and you can use Fs equals to 0.999. Oh, sorry, no need this, just wipe it. And then we can see the expected inventory actually increased, but not doubled, just slightly increased. And expected inventory takes up the days of demand actually drops. So that's actually the most important positive results. So the days of demand you hold actually significantly reduced when you merge the inventory locations, or you pool the inventory locations. And then you can see at the beginning, the save is significant from 2 to 3 territories. Then you save about 2.2 units, 2.2 days of demand. And until the 7 to 8 is about 0.3 days saving. So in that things, you need to make actually trade-off how many territories should be pooled. Of course, the more inventory locations pooled actually become more expensive, because you think about a location, central location for 2 or 3 different territories, the transportation distance will be closer. If you have 8, then you probably need to have a larger network, more complicated information sharing issues, and so on. So this is a trade-off making problem. So this is what we calculated expected inventory in days of demand. So it's expected inventory in units divided by expected daily demand. So example is we use 3.4 units divided by 29. Then equals to 11.7 days. So this value actually very important. The days of demand is related to the inventory cost. So normally we aim at a lower average inventory and a faster turnover. And then we continue to see the impact of location pooling. So we pool 8 territories, reduces expected inventory from 11.7 to 3.6 days, a lot. But pooling has no impact on pipeline inventory. Location pooling reduces demand uncertainty as measured with a coefficient of variation. So based on the Poisson distribution or demand, we can calculate the coefficient of a variation when you actually pool the inventory across different territories. So here, by definition, coefficient of variation is a ratio between standard deviation and the mean coefficient of variation. And then you can see the coefficient variation, the standard deviation for Poisson distribution actually is the square root of mean, and the mean of the Poisson distribution is itself. So the coefficient of variation is 1 over. To summarize the impacts of location pooling, we can see first, we can see the main benefit is actually expressed by expected inventory in days of demand. For example, if you merge from one territory to two territory, share the inventory, then the expected daily demand actually will be reduced. So you initially have a 3.4 divided by 0.29. Now you actually have 4.8 divided by 0.58. So this actually dramatically reduced. So we can see if you put 8 territories together, the inventory of days will be reduced to 3.6 days. So this actually directly lead to a stock turnover rate. So stock ratio, yeah. So that actually increase your stock turnover rate, then actually reduce the cost. So that's an intuitive result. But pooling has no impact to your pipeline inventory, or we say on order inventory. However, we should also know this saving from pooling inventory also needs the expenses from the delivery or transportation or storage, renting cost, and so on. And the next, location pooling reduces demand uncertainty as measured with the coefficient of variation. So now you can see, first we know the definition of coefficient of variation is a standard deviation divided by mean. So here is a table, we can just cross this out. And then the coefficient of variation for Poisson distribution will be 1 over square root of mean. Now you can see if you merge more territories, then the mean will increase. Of course, the COV will decrease. So let's see the impacts of location pooling. Third, the location pooling shifts the inventory service trade-off curves down and to the right. So how this is actually explained. So first, let's see shifts it down. So you can see when you're given the service level. So for example, we just choose one service level here, and then if you remember, we actually consider 99.9, so it's somewhere, it's very close to the 1. And then now you can see when you pull the inventories, then you actually reduce the expected inventory by the days of demand. So you can see this, for example, is 1, and this is 2 territories, this is 3 territories, and so on. And on the other hand, now we can see if you look at this given level of inventory, for example, at the inventory 4.2 days, if we draw a level line, now you can see for two territories merged, you actually reach a 97% of service level. But if you merge 3 territories, this green curve shows you actually reach a much higher inventory levels. So service levels. In that things we see we shifted down and to the right. So we can actually further explain that for a single product, location pooling can be used to decrease inventory. So we decrease inventory while holding service constants. Or so we hold the service constant, for example, this green line, or increase service while holding inventory cost constant, this orange line, or a combination of inventory reduction and service increase. So basically, if you go this direction. So our location pooling can be used to broaden the product line. So we have talked about how to merge the inventory across different territories in Medtronics supply chain. Now we can also talk about the distribution centers. So currently the company has only one single distribution center. So what if they could actually extend the distribution center into 2 or more? So here we have actually a plot to show the relationships between the number of distribution centers and the expected inventory. So now you can see with the increase of your number of distribution centers, your total expected inventory actually is increase. So this direction. So you have to be prepared that the coefficient of the variation actually also increase. So that's actually the impact of split the single location, single storage into multiple storages. In these things, you have to be careful to actually consider if you need to operate more distribution centers. Of course, there are the service level requirement or this transportation issues, so they may actually increase the responsiveness of your supply chain when you add more distribution centers, but normally it actually means higher inventory costs. So now let's see a second option for pooling. So we talk about product pooling. So we use a news window example. This is O'Neill example. It sells two. Assume they sells this company sells two white suits that are identical except for the logo silk screened on the chest. So it's basically it's the cosmetic difference. And instead of having two Harmer 32 suits, O'Neill could consolidate its product line into a single Harmer 32 suit that is a universal design, which we will call the universal Harmer. So this actually starts from the Harmer 321 and the Harmer 322 into a single universal Harmer. So this actually called product pooling. Basically merge two products into a single product. So the optimal order quantity for separate products. So here we have a surf hammer and dive hammer. So the order quantity for each of them will be 4,196 units. And optimal order quantity for universal hammer. And then we need to update the average demand and then average standard deviation across two products. So when you have two products, so the standard deviation will be the 2 square root times. So you got a new the average demand and the standard deviation. So the critical ratio will be same, so critical factor will be same, 0.85. Then the optimal order quantity would be the mean plus, so here is mean dash prime plus sigma prime times 0.85, which is 7,804 units. Then we can calculate expected profits. So we use underage cost times expected sales. So use overage cost times expected leftover. You can write the expected leftover, if you still remember, Nussweiler model should be the sigma square times I, so standard normal inventory function times I zeta. So here I 0.85 equals to 0.96. So that's how we calculate the expected inventory level equals to 1,670 times 0.96 is about 1,604 units. And then expected sales equals to the order quantity Qs minus your expected leftover inventory. This is about 6,200. That's how this value and this value calculated. So altogether we get the expected profits. So this expected profit actually is greater than initially the individual products expected profit. So in that sense, this actually is more profitable when you pool the products into a single product. Previously, we actually assumed the demand is independent, so two demands, So previously we assumed the surf hammer and the dive hammer, their demands are independent from each other. So here we actually try to assume the demands are correlated. When the products demands are correlated, actually it's very difficult to be solved. So here we try to analyze the important impact of correlation. So let's see how can we actually take advantage of the correlated demands. So first, let's see what is correlation. So correlation refers to how one random variable's outcome tends to be related to another random variable's outcome. So here we have the three scenarios. So if you see, this is a scenario 1. So this is a scenario 2. And we have a scenario 3. And in the scenario 1, we have the correlation coefficient actually is minus 0.9. So now you can see when, for example, the two products demands, so product 1, so this is product 2. So now you can see demands and the two products demands actually increases on the opposite direction. So when the demands increases for product 1, the demands for the product 2 are actually decreasing. So that's called a negative correlated. And the scenario 3 is on the other way around. So the coefficient is 0.9. So it's basically the product 1's demands increases with product 2's demands. So they have a positive impact to each other. And then we can also see the scenario 2, we see the coefficient actually is 0, or we see this is independent demands. So now the question is how this in scenario 1 and scenario 3's correlation actually affect your order or inventory decisions. So first, let's see the impact of correlation. So if we combine two demands with the same mean and a standard deviation, then the pooled demand has actually expected pooled demand is 2 times of average demand for each of the product. Standard deviation for your pooled demand actually is 2 times 1 plus correlation times sigma. So this actually previously when we have two independent items, so if we have independent items, then your standard deviation is square root of 2 times sigma. So now basically you will have a larger or smaller standard deviation. It depends on your correlations number greater than 0 or less than 0. There's a typo here, just correct it. So correlation. And then we can see the coefficient of variation of pooled demand is a new value. So by definition, the coefficient obviously is COV actually is 2. Is a mean divided by standard deviation times 1 plus correlation. Actually, times sigma over mu. So if you rearrange this COV, you get actually the new result. So that's actually the definition of correlation. Then we can see the result will definitely depends on how the demands are correlated. Is negative correlated or positive correlated? So there are actually series typos. So correlation is with 2R. So should be more careful for proofreading. Now we use this coordinate system to show this matrix to show the outcome of an inventory policy. So assume you have 2 order quantities for different items. So now you can see if you order Q units of serve hammer and Q units of dive hammer, then you can see you get 4 areas or 4 regions for different performance. So on the if we see this is area 4, so it's area 1, this is area 2, so this is area 3. So in the area 1 or the region 1, you have both items, both products have a leftover suits, so it's actually slow selling result. And in the A4, both items stock out, so that means the demands are both very high. And then in the A3, we have an A2, area 2 and area 3, we have 1 stock out and 1 left over. So that's actually the independent decisions or order quantities. So now let's see if you pull the 2 products together and produce a universal hammer and you order Q units. So what's the outcome? So first let's see on the this circled lines, this actually is the line for 2 products, the dive hammer and the serve hammer. Actually the total demand equals to Q on the circled lines. Of course, we see on the under this line you have, so under this is a diagonal lines, so we actually have leftover products. That's basically because under this line you have D1 plus D2 actually less than Q, and above this line you actually have D1 plus D2 greater than Q. So then that things leads to stock out. So that's actually the outcome for product pooling. That's also why we are interested in pool the products, because on this D1 plus D2 lines is basically is so this line shows your product is actually negative correlated. So if your product is a positive correlated, then you have to consider the direction of another. So another line, actually we cannot take advantage of the positive correlated demands on this direction. Now let's see how can we actually take advantage of the negative correlated demands and generate optimal order quantity. Okay, now let's calculate the optimal order quantity. Now we consider the demands are correlated. So we start with the universal hammer products. We have the mean calculated previously, standard deviation calculated. We know the underage cost, overage cost, and then we can calculate the critical factor. So it's called a critical factor, will lead to your optimal order quantity. So with a correlation 0.2, so this is a positive correlation, and your optimal order quantity will be determined by your mean and standard deviation. So when you calculate the standard deviation, then we actually need to recalculate your correlations into your standard deviation. Now you can see the positive correlation leads to a higher standard deviation, which is greater than previous 1670. But we can still use this number to calculate the order quantity, which is 7,939, is also greater than the previous 7,834 or something. And then if we continue to calculate expected profit from these results, then I do not repeat how to calculate leftover inventory. So basically is what we have done many times. Expected sales is Q minus leftover inventory. And then we calculate the total expected profits. Actually is less than the universal independent demands, order quantities. So this actually is less than 4,063 something from the previous calculations. And then we consider the second scenario. We assume the correlation now is minus 0.7. So this is a negative correlated. So negative correlated demands. So again, we need to recalculate standard deviation. The mean will be same, and then now you can see now we have a 1 minus 0.7, which is actually smaller than the previous standard deviation. So now we got a 915 standard deviation. So your order quantity will be 7,162. So now this is the order quantity for the negative correlated demands when you try to pull the products together. So now you can also see the expected profits will be 485,000. So which actually highest profit so far we have seen from this case or from this example. So that means the negative correlated demands, if you put them together, will definitely give you a better, improve the performance of your order decisions. So if we generalize the analysis in the previous examples, so we can observe when you increase the correlation between the products from negative -1 to positive 1, you actually see COA, the coefficient of variation, actually increases. At the same time, the expected profit will decrease. So this actually shows how you can actually maximize your profit when you try to pool your products into a universal product. In this example, the completely negative correlated demands will generate the highest profit. So the completely positive related items will generate the lowest profit. Therefore, that's very important to actually study if the products are correlated or not correlated. So it's completely uncorrelated or independent when your coefficient is 0. Otherwise, they can be negative correlated or positive correlated. Once you observed that you have the items which are negative correlated, then you probably can think about pool the products into a universal or unified item. But they do have actually some drawbacks you need to pay attention to or be aware of. For example, if you actually merge different products into one. For example, you have mountain bike, you have road bikes, and then you decided actually to only offer hybrid, then you probably will lose some functionalities of mountain bikes or road bikes. So you not necessarily satisfy all the customers' requirements, given some bikers actually need the special functionality in your separate products. And also, you produce a universal products may also become more expensive, depends on the design and the components and extra requirements. And also, the product pooling may eliminate some brand and price segmentation opportunities. So that's clearly, we also suggest the product to be differentiated in order to actually segment the market to extract the highest profit or the revenue. In that sense, product pooling is all about balance the variety and the cost. One thing we need to mention is also called postponed differentiation. So that actually means if you decided to produce a universal or merge or pool the different pool different products together into a universal product, then you actually can also later on to distinguish these products into the original two separate products again. If you could actually do some light manufacturing or other assemblies to actually deliver the more diverse product to your customer later. So that's actually also addressed in the textbook. So you should look into that if you think it's interesting. So another pooling strategy is called lead time pooling. So this actually somehow related to the location pooling. The textbook give you the detailed discussion about this strategy. So we basically here just briefly introduce the strategies. And then now we consider two systems. So in the figure or the graph here, you can see we have two supply chain systems. In the first upper system is called the current system, direct from supplier. So supplier delivers items directly to individual stores. And you have a proposed system suggests you to add a retailer distribution center. So here, distribution center. So try to centralize the inventory in a distribution center for multiple stores. For example, in this case, there are 100 stores. They add one distribution center, and then the lead time between retailer distribution center and the stores are 1 week. And then the lead time from supplier to the retailer distribution center remains the same, 8 weeks. So now the difference is now in the proposed system, you have a lead time of actually 9 weeks from supplier to your individual stores. And now we will try to see if it makes sense to have these retailer distribution centers. Now definitely this lead time for 8 or 400 stores actually merged into one lead time. So in the current system, you actually need to think about 8 weeks lead time for each store. And if we call it L1 and L100, L2, Ln, now you actually can see we have only one single supplier to distribution center lead time. So it's kind of pooled, but again, we add extra lead time for 100 stores. Let's see the performance or the outcome of such a change. So now we are looking into a case. So the weekly demand at each store is Poison with a mean of 0.5 units, and the target in-stock probability is 99.5%. So in the distribution center, the demand is normally distributed with a mean of 50 and a standard deviation of 15. So this is from historical data. So basically, it's a realized average, mean, and standard deviation. And then you can also estimate this standard deviation from your stores. So if the demands were independent across stores, then the DC, the distribution center demand, would have a standard deviation of 7.07. So this actually is calculated across 100 stores. So in the textbook, you can see the detailed calculations. So briefly saying, so each store has a 0.5 average or the mean demand. So it's a Poisson distribution. So that means standard deviation should be 0.5 times 100 stores. So that's why you got a 50 square root. Then the analysis shows this actually is not necessary. It's a correct standard deviation. So from the more analytical analysis, they actually figured out the standard deviation should be 15. So on this slide, we did not give you the calculation details. So here we conclude the pooled lead time or lead time pooling reduces the retailer inventory by more than 50%. How this is calculated, we can quickly have a look. So in the initial or the current system, you have 8 weeks lead time. You need to think about L plus 1 lead time demands. So now you have actually average demands for these 9 weeks will be 4.5. And then from the normal, from the Poisson distribution table, you actually can find out when the mean is 4.5. So your order up to level S should be 10 units. So in order to get a service level equals to 99.5%, so that's an initial requirement. And now if you put this, if we build this centralized distribution center, then let's see how this order up to level will be changed. So let's see now if you have this centralized inventory position, which is called the retailer distribution center, then your lead time actually equals to, so the lead time equals to 1 now, and then this required average demand over lead time plus 1 is actually 1 plus 1 times 0.5, which is actually 2 units. So that's actually the current system. So this is a new or proposed system. And then if we still consider service level 99.5%, then you can actually find S is about 4 units. So that's actually how you analyze the difference between these two systems at the store level, or we see retailer inventory. So actually, although this is a consolidation of distribution, consolidated distribution is quite effective, but normally it's not as effective as location pooling. So you can, if it's possible, you can always use a location pooling to analyze this problem. However, by consolidated distribution, keeps inventory near demand, thereby avoiding additional shipping cost and allowing customers to look and feel the product. So that's actually the advantage when you think about to add extra distribution facility. So the benefits of add extra distribution facility. And in table of 17.4 from the textbook, now you can have a quick comparison for these different strategies. So we did not actually do the location pooling calculations, but the results are here. If you're interested, you can do the calculation. So we mainly see the direct delivery for your items. So expected total inventory at the stores is actually 650 if you continue to do the calculations for IS across 100 stores. And the centralized inventory supply chain, you actually can also calculate the, so if this is S1, now you actually have S2. So if we name this as S2, this is S1, and again you have actually 100 stores. So now you can continue to see the expected inventory at the distribution center. Of course, there is no distribution center current system, and in the centralized distribution center, then you use a normal distribution. If you remember, we can also calculate your expected service inventory levels for IQ, and now you can actually times the standard deviation. That's how you calculate this centralized inventory in the distribution center. If you purely do location pooling, then you do not hold any inventory in the distribution center. So you only have this centralized storage. So you do not hold any inventory in retailer stores. So that's actually the different strategies comparison. So it's not very detailed in these slides. Try to read the textbook to figure out all these numbers. If we only compare the direct delivery and the centralized distribution center, then we can see add one centralized distribution center still actually reduce the average inventory, so from 650 to 466, although now the lead time actually is longer than previous 8 weeks. Here we actually have two figures. One is 17.10, one is actually 17.11, so that's two different figures. So in the figure 17.10, we're talking about the inventory with a consolidated distribution supply chain. So we have different types of inventories. So now you can actually see you have the blue lines, which is a retailer. So this is a store level inventory. So you can see the standard deviation of weekly demand across all stores increases, but your retailer store level inventory keeps the same. And then you also have the red lines is a retailer inventory plus the pipeline, or we call it on order inventories. We have only actually 1 week lead time, so you normally have 1 week one order on the way on the pipeline. So if you add this distribution centers inventories, then we got a total inventories. So here this a triangular black curve shows the retailer or store level inventory plus pipeline inventory, and then plus DC inventory. So that's when you increase the standard deviation of the demand across all stores, so of course your distribution centers standard deviation will increases. So that's why your total inventory will increase. So here we can see the most important inventory is your distribution centers inventory. So on the right hand, we have the figure 17.11. So these are the different curves. So we have this original blue curve is from the current system, or we see the direct delivery from supplier to the stores. And then the red curves actually, red lines actually is consolidated, or is proposed inventory systems. So now you can see if you pull the lead time together, and when you're with the increase of your lead time on the horizontal axis direction, your total inventory actually increase not that significantly as the current system. Of course, you can see when your lead time actually is shorter, the average inventory for the current direct delivery actually is performing better than your pooled lead time system. So that's all about analysis, analytical comparison when you actually choose different type of systems. It's not always like if you pool the lead time together, and then you will get a lower inventory. So you have to look into the impact of the length of lead time. We actually have another strategy called capacity pooling. So I decided to actually skip this strategy because it's actually mainly for production and manufacturing applications. So we're talking about how to add the flexibility into your system, because for example, when you consider the product pooling, we should also consider the postponement of the product pooling. So capacity pooling, we actually more focus on the flexibility. How can you add to your manufacturing facility, which is not a focus of your program. So we decided to skip that. Of course, if you're interested, you can just check the textbook and know about it. So here we just summarize when you actually should consider pooling. So we call it the pooling principle. So pooling of customer demands along with pooling of the resources used to fill those demands may yield operational improvements. So that means they actually need to think about if you can save the resources, and then this is a direction will help you to reduce the average inventories. So if you actually do not reduce the inventory locations, or shorten the lead time, or add other reduce the variations of your demands and so on, so they may not always benefit. So look into the problem and pursue the different possibilities. So together with a pooling principle, suggest you to read the article. So the article have a brief summarize about pooling strategies.